Hello everyone, can you hear me? Yeah, I'm sorry I couldn't be there. I got a bad flu and now I have to give the talk online actually. Yeah, right. Missing all of friends and everything. So I heard the conferences very well. I have been trying to follow it on YouTube and I'm thanks to Manjari and all the organizers for giving me the opportunity to talk. Actually. Uh, Today I'm going to talk about something which was supposed to appear a long time ago, but we got so engrossed in it that we kept exploring it a little bit more and so on. Uh, so this is going on using ideas of Anderson localization to explain neutrino masses. Um, okay, now BSM physics, as a landscape of a lot of beyond standard model physics, there are a lot of wonderful ideas and supersymmetry, extra dimensions, strings, composite. But sad to say that after the Higgs discovery, it has transformed itself to barely see physics actually. So you don't really see it. You don't have any signatures or anything. Okay, but it doesn't stop us to start speculating or especially to look at if in all these models, is there a place to explain neutrino masses? Because we know the standard model is not complete, and especially at least for the neutrino case, we need to explain the atmospheric and solar mixing angle as well as their mass scales essentially. The mass scales are extremely low compared to the electron mass scales, about 6 orders of magnitude. And they typically, it looks like that we are having mass scales which are exponential, like an exponential series essentially. So we have 10 power minus 12 uh, suppression compared to what is there are the present work is again trying to explain these things with a couple of new ideas. It's a combination of two new ideas, sort of new in the sense they are about 5 6 years old actually. One is this is a pretty old thing in stringy landscapes, essentially that you can have randomness or disorder averaging or disorderedness in stringy frameworks, which means that essentially you can have couplings which are random in nature. You can also have it in masses. Essentially, you can also have in masses. So, in terms of effective field theories, which derive from these things, quantum field theories, you can have randomness in your couplings. Essentially, you can have randomness in your couplings and randomness in your mass terms, etc. There is a nicer version, field theory version of this by Dinas and Kumar, where instead of using strings or anything, you can have dark sectors with large symmetries. Essentially, the the vacuum structure of the theory contains extremely large symmetries, such that the you can show that randomness is generated uh, in terms of this large symmetries in the if you have a large symmetry, you can have a vacuum structure in which the mass terms uh, uh, and the couplings can take any values within a certain region, essentially. Now, so you have field theories which give you randomness, effective field theories, not okay, effective field theories which have couplings and masses which are random. Now, there is also a simultaneous idea that you can use this uh, uh, randomness in couplings or in mass terms to generate exponential hierarchies in masses, essentially. It's a basic idea of Craig and Sutherland, which I'll explain to you. So here, look at this is the Craig and Sutherland model, Craig-Sutherland model, in which you have a bunch of fermions, which are in 4 dimensions, which are coupled with each other with the next neighbor. These are mass terms, essentially. I'll explain to you in a second. And vice versa. So both on the left, right, and right term. So you have mass terms which are like this, which are like nearest neighbor mass terms. So here is your kinetic action, and here is your mass matrix. This mass matrix has diagonal terms which are given by epsilon, and next to nearest neighbor mass terms, which are also TIs are dimensionful couplings. Epsilon I also are dimensionful couplings, which are masses, which are diagonal mass terms. TI are, this is just to put it in Anderson language, essentially, just to put it in. TIs are next to nearest neighbor mass terms, which you can represent the full mass term as this particular thing. Now, what happens to this if you have a chain like this? Once you have make them random completely, because coming from this fundamental theory in an effective theory, this is an effective theory. Once you have this thing, what happens is in the limit, if you vary the epsilons, the diagonal mass terms between a range which is 0 to 8, all the wave functions of this particular Lagrangian are completely localized. So this is the sites. This can be nicely seen in this graph here, in which I have plotted on the x-axis the site number 1, 2, 3, 4, 5. This is for 8 sites. And W is equal to 3. These are in the units of TeV. And so when you randomly generate between, all the modes are completely localized. And so this is completely different compared to other models of extra dimensions or clockwork models or so on. So in which only the first mode, the zeroth mode is localized. In this case, exactly like in Anderson localization in condensed matter, all the modes are completely localized. And the efficiency, so this makes it much more predictive compared to the other models, and you can compute these predictions. Now you can actually make it, you can actually look at how good is this localization, in the sense that is it so efficient? How much is the hierarchy you are going to generate it? So you can take, say for example, only one chain, in the sense that you only take only left to right. Say for example, there is a zero mode in this case, or you can take left right and right left, but don't really make these parameters random, but just make them universal, completely universal. In both the cases, you have localization only of the zero mode, and the localization, you want to see how good is this localization of the zero mode versus the modes of this Anderson localization. You can have a check. So you see, you can generate hierarchies of the order of 10 power minus 20 in the case of Anderson localization. It's extremely efficient. So this is so here I compared with one with the zero modes of the random clockwork mode, and then random site, meaning essentially epsilon I, which is random, and random coupling, which is also the T, which is the next to nearest coupling, which are random. And then if both of them are random, you see that you can really generate very large hierarchies. Now in the standard model, we don't need such deep hierarchies, but we have something like 10 power minus 12 hierarchies, which are good enough for us to explain all the fermion masses and mixing angles. To begin with, I'll start with neutrino masses and everything, but a little bit more of exploration of the localization a little bit more. Now, on the left hand side here also, I just want to show you that how does things look like if I set all of them to be uniform. So the modes are completely delocalized. So you can plot them on the sides and they're completely delocalized. Whereas in the presence of disorder or randomness, they're completely localized, essentially completely localized on the right hand side. Sorry. Now you can go further and say what happens if you have next to next and next to next mass terms in your model. Okay, so you can go further and further, and you can link all the possible in the chain, essentially all the possible fermions in the chain. You can fill up the entire mass matrix. In this case too, you have localization of only of the zero mode, but the moment you turn all of them to be random, all of them get completely localized. This is the case I'm talking about, in which suppose if I take 8 sites and make links to all the possible fermions, essentially. So the mass matrix will look somewhat like this. You have the diagonal mass matrix, the entire mass matrix is full, but we need something like a uh, like a like an organization principle. So here we have taken the organization principle such that the coupling is changed by an order of B parameter as you keep going away from the diagonal. So if you move one step to the diagonal, you pick up a factor B. 2 steps to diagonal, you took a factor B square, and so on. So on, you fill up the entire mass matrix and then ask for localization of the modes. Yes, there is still localization of the complete modes, essentially. So what we learned is that randomness, you can do the same thing with different geometries, essentially. Other geometry which we realized essentially is something called a Peterson graph, which is not completely. So you can look at different geometries and corresponding mass matrices. So your mass matrix is represented by a very nice geometry. Okay, and so you have a graphical picture. So you have, again, in this case, you have part of them are next to next nearest neighbor, and other part are not next to next nearest neighbor. But then you have an organizing principle similar to the one which I showed you earlier. This is called a Peterson graph. So here you have all the diagonal terms which are completely epsilons, and the next to nearest neighbor terms which are completely described by this particular case. The Peterson graph is very interesting in the sense that, in the if you take all of them to be universal, if the mass matrix, all of them to be all same, all the epsilons to be same, all the G parameters to be same, all the B's to be same, you get half the modes localized on the left, half the modes localized on the right. Okay, so sort of half of the sites are really, so in between there is an intersection. Sort of a lot of the modes are sort of things, essentially. So along the left, essentially half the you can see on the left hand side graph. But the moment you put in randomness in all these couplings, you have all the modes localized at whatever site we don't know. Now, if you want to do phenomenology with this phenomena, one of the important issues is how do you identify where it is localized? Essentially, you have no idea because of the inherent randomness into the picture. You don't know where the mode will be localized. So, which mode should be coupled to give you the right neutrino mass, essentially? So, which mode? Where do you utilize? How do you utilize this exponential hierarchies which are being generated, essentially, in these couplings? Now, okay, I can, okay. So in the strong localization limit, in the sense that if the diagonal elements are very, very strong compared to the off diagonal elements, it seems sort of you have universal features which are for all. So let me talk about neutrino masses and mixing, which you can explain to all the flavors, essentially. Are independent of the geometry of the chain. So you can think of the chain to be whatever chain it is. It can be Peterson graph. It can be completely non-local graph like this, or some other graph like this. Anything, whatever be the case, you have some universal features which are essentially saying that you can get neutrino masses. So, for example, the way you get neutrino masses for the Dirac case, you can do the same thing for Marano case also. Is you take the R1 mode at the left, you need at least uh, uh, the left mode. If you have two modes, the lightest mode on the R1 mode, and couple it with the standard mode right-handed left-handed neutrino, and take the last mode left hand LN mode and couple it with the right-handed neutrino essentially. So this gives you a sort of Dirac neutrino masses for the neutrinos, and the sum result is, so you need some three such chains for the case of three neutrino masses. So the sum result is that you can explain neutrino masses of the order of EV in this case, but the mixing angles are completely anarchical. So the resultant mixing angle, the randomness nature also follows through this particular case, and the mixing angles are completely anarchical. So you have a prediction. So this is independent of the geometry. You can take any geometry you want, a Peterson graph or whatever graph you want to take, and write a corresponding mass matrix for it, and then get neutrino masses like in the case I had written. You can do the same thing with Marano masses. In the Marano masses, it's much harder to get neutrino mixing angles. But you can do much more. This is the same. This is for the Marano masses. You have Lagrangian in this particular fashion. You add a Marano mass term here essentially. I'll come to the if I have time for the Marano masses. To summarize, the strong localization limit has a prediction that you have anarchical mixing angles for neutrinos, which sort of I don't think it really fits the data very well, but it's a prediction of the theory essentially. But it doesn't mean that we had to rule it out. No, the actual thing is we can inverse it. We can take the limit of the weak localization or the weak disorder limit. In this case, what happens is you don't have a complete localization of the wave functions. You don't have complete localization of wave functions, but you can have wave mixing angles which are localized. So you don't really need wave functions. You don't really have wave function localization, and like an Anderson-like effect essentially. But you can nicely generate localized mixing angles which fit the data very well actually. So here you see theta 1 2, theta 2 3, and theta 1 3 fitting the data very well, and the masses also pretty well. The weak disorder limit is an example where you can show it essentially, and this you can show it in. This works very well for the first case, the Anderson, the nearest neighbor only. It works very well. The variance is extremely small, but the moment you start plugging in the extra terms, essentially, if you are starting seeing the other nodes also beyond your the diagonal terms, the variance starts increasing, but you can still fit it. But of course, there is no real localization of the mixing angles in real sense. Okay. For the Marano case also, you can get, yeah.
You have 10 minutes.
Yeah. Okay. I was hurrying up because I thought I had less time actually. So sorry. Yeah. For a Marano case also, in the Marano case, okay, I can explain the Marano case a little bit. So here you have the kinetic term, and then again add the same Dirac-like action term, but you break the lepton number by a mass term of this particular type, the W essentially. W is the same W which appears in the randomness essentially. The scale of the localization, the scale of uh, the randomness also will break the mass of the also is the scale of the randomness of the scale of the Marana mass scale. Now, in this case, also, uh, but in the weak disorder limit, that means epsilon are less than or equal to the off diagonal terms, or all the mass matrix elements are roughly close to each other. Essentially, you can localize the mixing angles. You don't localize the wave functions. You don't localize the wave functions, but you localize the mixing angles. Here too, the reverse is case compared to the Dirac case. The variance is larger for the local case compared to the Dirac case. Now there is a couple of caveats which you should remember. One thing is that one of the conditions is that if you really go for there are some free parameters in the way neutrino masses are generated essentially. So these are considered to be order 1. So for example, these Yukawa couplings are taken to be order 1. Now, if I insist, if these Yukawa couplings are also completely random, then even in the weak disorder limit, I don't get localization of the mixing angles. So in principle, I'll only get anarchical mixing angles because essentially I'm setting them to be completely random. That it essentially becomes it's understandable because it's like taking an anarchical mixing matrix, anarchical mass matrix, and so on. So you take them to be order 1, essentially some order 1, and so you get nice localization of the mixing angles. Now you can generate while you can explain the neutrino masses and mixing angles very well, you can easily explain the charge lepton mass matrix as well as the hadronic sector. Okay. I'm not going to share any results from the hadronic sector because I'm focusing on neutrino masses, right? Neutrino flavor. Now, phenomenology. And one of the important things is phenomenologically, is this model viable? As I said, this model is extremely predictive in the sense that all your modes are fixed, their masses are fixed, and you know what is your lightest mode, and you know what it is essentially its couplings are, and so on. So we calculated, say, one of the easiest things, first things to do is calculate radiative decays of muons, essentially, which is or leptons, charged leptons. So we computed the limits coming from mu going to e gamma, which are the strongest ones, essentially. And we show that this is within this thing. A large part of the region of the parameter space is already, this is a heavy model. This is the model, it sits at TeV scale. A large part of the model is already being probed by mu going to e gamma, essentially. So the constraints become weaker for partially local and non-local cases. So, so this is interesting in the sense that if you take completely non-local model, like means the mixing comes dominantly coming from some non-local interaction, non-local mass from very far away master. The mixing is weak by the time it comes here. So it couples to the leptons and the W very, very small. And so the mu going to E gamma is also very weak, essentially. The mu going to E gamma and the collider signatures are also very weak. So I stop here, essentially, that so the outlook is randomness in coupling can lead to exponentially hierarchical couplings. In the regime of strong coupling, the geometry of the mass chains does not matter significantly. They predict hierarchical neutrino masses and anarchical mixing angles for both Dirac and Marana scenarios. In the weak coupling regime, the geometry does play a role and can be chosen carefully to localize the mixing angles. And we also looked at rare decays and collider signatures for for all geometries essentially, for strong coupled systems essentially, and they become weaker for non-local and partially non-local cases compared to the local case. Okay, that's all I have to say. Thank you.
Thank you. Any questions here?
Hi, thanks for the nice talk. So my question is, how stable is this localization if you add, let's say, one loop corrections?
Pardon?
If you add quantum corrections, let's say at one loop, how stable is this localization remains? Is it still localized or something changes? What happens?
Quantum corrections. Now the question is, these are effective field theories. Okay, so you have to think in terms of effective field theories. Now, if you because you're averaging over disorders, essentially, you're averaging over all the randomness in the couplings. Okay. Now, if you want to still compute, you can compute. It depends on the model to model. Essentially, if you think in terms of purely clockwork like scenario, you know that radiative corrections can become very important in the clockwork scenario. Essentially, like okay, in this case, we computed radiative corrections. Say, for example, mu going to E gamma or something. Essentially, we computed corrections to the Higgs because so you average out all the, you fix all the number of modes. You fix the localization may not be. Okay, I understand your question. The localization is not stable because the localization itself is changing with the random number. Okay, if you change within that range, okay, it is localized. As long as your epsilon and t's are there, all the modes are localized. Now, which mode is localized where there is a randomness, essentially. That is only randomness. The localization itself is sort of fair.
Thanks.
Harry?
Hi, Sudhir.
Yeah.
I got confused with your notation. You had L and R and also a psi. Would you mind clarifying? So L and R are the two neighboring sites, I suppose, the fermion.
LR and R, okay, I can
And
share.
then you also had the psi, and those live at the site or what?
Okay. So
I guess
L and R,
see
okay, I can
what
just
is the
show.
role, what is the role of psi?
No, psi I introduced only. Psi is L and R as long as we are talking about Dirac cases.
I see.
Okay. For the Marana case, I introduced a new fermion. Sorry. I'm
So
going
if you
up.
can show in the Dirac case, maybe that will be helpful.
Right. In the Dirac case, there is no psi.
Ah, I see. Okay.
Okay. In the Marana case, there is a psi, which is a new fermion I introduced. Okay. X just to break the lepton numbers.
And that doesn't get an I index. It's just one single field or what?
You can, this is for one generation.
Okay. So there is a single fermion which
Right.
couples to L. One.
Right.
Okay.
Yeah,
right.
L1.
And what is its role? Why do you have that?
No, you want to, its role is essentially to, this
so
is exactly like seesaw.
Okay. Yeah. Got it.
And, there's nothing else.
Okay. It breaks the lepton number
Lepton number and just, this is seesaw. This is Dirac.
All right.
It's like right-handed Neutrino.
Okay. Sorry, can I ask one more question?
Yes.
Okay, so the localization itself, I guess it is obvious, but I don't see it. If you have a very strongly localized, you have a very suppressed mass. Is that
Exactly.
okay? And is it
that is purely because
right.
no, if you have a very strongly localized, the hierarchy generated is very large. It can be okay if it is very strongly localized. So you can think in terms of the wave functions. The wave functions
Right.
are very strongly localized. So you are coupling to the tail end of the wave function, and it's
So
exponential.
I couple to which one? To the Higgs, is it?
Depends again. Yes, you couple to the Higgs.
And so its coupling to the Higgs would be very suppressed because that lives only
Yeah,
on
because you're
or something.
imagine exactly like extra dimension.
Okay. That Higgs
Okay.
lives only on
It
an
will be-
element.
so Higgs can live in. So the left wave function you put it on the right hand on the one
Okay.
brain. The
Yeah.
right wave function you put it on the another brain,
Okay.
and you can put the Higgs anywhere you want in the bulk or whatever it is. Essentially.
Okay.
And that gives you a very small suppression because the wave function overlap is very small.
Okay. All right. Thank you.
Any other question? Yes.
Hi. I just wanted to understand, do you decide in advance which site you want to couple the Higgs to? Because you said that the localization can change. So, like, unless
Right.
it's going to be suppressed, like if you decide in advance, I'm coupling to the, let's say, 10th site, and then is
Right.
it robust that
So
it's
once
always
once your number of sites are fixed, okay. So there are two ways. Either you fix, you can put it in any site you want. You can do it at any site. This thing works.
okay?
This thing works.
You're saying you don't know where it will.
As long as you
It's
put,
localized on the.
yeah. As long as you put one wave function on the left and one wave function on the right.
I
Yeah.
see.
Yes.
Hindu.
No, so just to continue that question. So how do you know that that object is actually a neutrino which is very light, because your masses are also random, right?
No. I identify my left-handed neutrino. Okay, my masses are random in the sense my masses are random. It's true, but once they are localized, the couplings are fixed, and the couplings to the Higgs give you the neutrino masses. Okay, once the fields are localized, I know what their couplings are. So the couplings you can demonstrate with respect to the localization length. Okay, so if you know the localization length, I don't know when I must have written it somewhere essentially. So the localization length gives you what is the coupling which gives you the thing essentially. So
So that's why you want it to be at the two endpoints, is it?
yeah, exactly at two endpoints.
Oh, I see. Okay. I see. Okay. Thanks.
Any other? Yeah. Sand.
Hi, Sudhir. If there are sometimes it happens that in an Anderson localization, the localization of the modes depend on how many sites you have in the system. So,
Right. The lowest number of modes we were able to have localization, meaning efficient in the sense we were looking at localization of the length of say 10 power minus 6. Okay? A hierarchy of 10 power minus 6. We were able to get it with 8 number of sites.
Okay. Okay, thanks.
And if you increase, you can get, like I said, if you can play with and you can really get very large. Yeah. So the number of modes n is equal to 8 is calculable, so we can do it very easily.
Yeah. Okay, thanks.